This is the first lesson of Chapter 9. We're going to be talking about cell growth and reproduction. So these are some of the key questions that we're going to be addressing in this chapter. And we'll get to some of these today in this first lesson, including why are cells so small? Why don't cells grow indefinitely? And what happens to a cell when it stops growing? So let's dive right into the first question, why are cells so small? One of the reasons why cells are so small has to do with diffusion, which you should recall we've learned about diffusion. It's the process by which molecules move from an area where there's a higher or lower to lower concentration. As illustrated here, this is like a timeline, so if you read it from left to right, you can see that on one side of the lipid bilayer or cell membrane, there's a high concentration of this particular solute. So over time, that solute is able to diffuse directly through the cell membrane in an effort to reach dynamic equilibrium, which will be shown on the far right. So diffusion limits cell size because a larger cell is going to need more materials to support it, like more food basically for the larger cell, and ultimately then it's going to produce more waste that it has to get rid of. So it takes a lot more to support a larger cell, so it's not really ideal to be too big when you're a cell. It's better to be small. And also the distance that those molecules have to traverse inside the cell to either distribute themselves if it's food or to escape the cell if it's waste. So in general, what we need to learn and take away from this is that for a small cell has better, or you could say better or faster, the diffusion than a larger cell in general. Okay, now another factor that's going to limit the size of a cell is its own genetic makeup and what that cell is destined to become or destined to do based on the DNA code of that cell or the organism that contains that cell. So cells, although it's better to be small for a cell, cells do have growth, but there are limits to their growth. So now we're going to address that second question that we laid out at the beginning, which is why don't cells grow indefinitely? What is going to limit their growth, in other words? So for this, we have to have an understanding of the surface area to volume ratio of a cell. And maybe you've heard of these terms before in a math class. And we will do a little bit of math today, but don't panic. We'll go through it together and it won't be too crazy. It's basic stuff. When you know the formula, you just plug and chug. But we're going to be looking at how as a cell gets larger, the surface area to volume ratio decreases, and this decrease can cause a serious problem for the cell. It's actually better for a cell to have a larger surface area to volume ratio. Let me make a note about that. So to model this and to prove this concept of why it's better to have a larger surface area to volume ratio and also why it's better for the cell to be small, we're going to do a scenario with 3 different theoretical cells. And those theoretical cells are going to be the shape of a perfect cube, just so that we can use these formulas easier for surface area of a cube and volume of a cube. And we're going to calculate the surface area to volume ratio of each of these cells, starting with this one that's a 1 by 1 by 1 millimeter cubic cell. So let's first start with calculating the surface area. If you recall from a math class you might have taken, to calculate the surface area of a cube or a box, you would imagine cutting it open and unfolding it so that all the sides would appear. And you're basically just taking the surface area of each side and adding them up. Now we're going to disregard the flaps, even though they're shown here on this illustration. Just ignore those. So we do need to know the formula for surface area, which is of a cube, that is. It's 6s cubed. So 6 sides, 6s squared. So we're taking basically the area of each side, which would be length times width, but because the length and the width are the same, you could just call those dimensions s. So it'll be like s squared, s squared, s squared, s squared, s squared, s squared. So, or 6s squared. Now for this cube, the side is 1 millimeter. So now we're going to plug in 1. One squared, 6 times 1 squared. Remember your orders of operations, so we need to do the exponent first. So now it's 6 times 1 and just 6. Okay, so the surface area of this cube is 6. Now we need the volume. All right, so think if you can remember what the formula is for calculating the volume of a cube. Maybe you remember volume of a box, length times width times height. Well, that's the same. However, we don't have different dimensions for length and width and height, so you could just call them all s. S times s times s, or s cubed. All right, so now plug in 1 for s to the third. It's like 1 times 1 times 1. It's equal to 1. Okay, so the volume is 1. The surface area was 6. Now we can calculate the surface area to volume ratio. It's simply going to be 6 to 1. You can write this as a ratio, or you could say it's 6 over 1, like a fraction. And the reason I'm showing it that way is because when we compare the other 2 cells that are also cubes, but larger, that'll be easier to work with, having them as fractions. In fact, even better if you write it 6 over 1, with the denominator being all the same. Okay, so now we're going to repeat this for the other 2 cells, the 2 by 2 by 2, and then a 3 by 3 by 3. So now would be a good time to pause your video and see if you can work these out yourself, and then come back and check. And for the interest of time, I'm going to pause and do that myself, so you'll just see the answers instead of me talking through it and eating up time here. Okay, so here is the worked out surface area volume and surface area to volume ratio for the 2 by 2 by 2 cubic cell. I came to a surface area of 24, volume of 8, and a ratio of 24 over 8, which reduces to 3 to 1. So this is where I was saying that it's important to have the same denominator so that you can compare the cell to the previous cell. Now we're going to do another scenario with the 3 by 3 by 3 cell. So go ahead and work out the surface area, the volume, and the surface area to volume ratio for this cell scenario here with length, width, and height of 3 millimeters each. Okay, here's the final work for the 3 by 3 by 3 cell with a surface area of 54, volume of 27, and a surface area to volume ratio of 54 over 27, which reduces to 2 to 1. Okay, so now it would be helpful to look at these side by side, the surface area, the volume, and the surface area to volume ratio for those 3 cell scenarios. And in fact, in your course packet, there's some places where you can take notes from this lesson and also record this data in a table, but I'll lay that out on the next slide. So here is the synopsis of the data that we gathered from that activity of comparing the surface area, the volume, and the surface area to volume ratio of the 3 progressively larger cells. So what the take homes here, we're trying to show why, first of all, it's better to be a small cell as it relates to the surface area to volume ratio. So as we previously discussed, having a larger surface area to volume ratio is ideal for the cell for best diffusion. So we indeed showed that the smallest cell had the largest ratio of 6 to 1. And as the cell got larger, the ratio got smaller. So the issue here, why this happens, is that as the cell gets larger, the volume increases more rapidly than the surface area. As cell size increases, volume increases more rapidly than the surface area. And this poses a problem for the cell because although the surface area around the cell is also increasing, and this is the cell membrane or the cell wall, this is where the materials can enter and exit. But if there's a lot more volume inside, that's more strenuous for the cell to support itself, to get enough food or release the waste that builds up. So if you notice here, like let's show what happens when the cell size doubles from like the first cell to the second cell. When each of the lengths of the sides doubled from 1 millimeter by 1 millimeter by 1 millimeter to 2 by 2 by 2, what happened to the surface area? Did it also double, or did it increase by a different magnitude? Surface area went from 6 to 24. So that is a 4 times increase in the surface area. Is that the same magnitude as the increase in volume? No. Volume went from 1 to 8, which is an 8-fold increase. So that proves what I just mentioned about the fact that as the cell size increase, the volume increased more rapidly. It's not proportional to the increase of the surface area. And that's going to be exacerbated even more if we compare the 1 by 1 by 1 millimeter cell to the 3 by 3 by 3. So we're just going to hop from the first one to the third one now and see how that differs. Let me change the color of the pen. Let's do teal, I guess. Okay, so going from 6 to 54, what is that? 9-fold increase. And how does the volume compare? From 1 to 27, 27 times. Okay, so again, the same thing occurred where the cell got bigger, volume increased more rapidly, but even more pronounced was that change from going from 1 millimeter cubic cell to a 3 millimeter cubic cell. Okay, in our next lesson, we'll be looking at the other aspects of the what happens now. If the cell can't continue to grow too big, why does it stay small and how does it maintain that small size?